Okay, so the plan for today is to get through our next two sections on multiplying and dividing polynomials. Again, I think we're still in kind of review territory. We really should be for a little while now, so this should look familiar from some previous work, but we're brushing up on these topics, maybe going slightly more into depth um, than you may have seen in a previous course. So we have quite a few administrative details for today. Note that the Unit 1 exam grades are updated, so if you haven't seen your updated grade on WebAssign, make sure to go in and check that. Sorry, I'm having like a terrible allergy week this week, so I might be rubbing my nose throughout the lecture today. Combination of fall and leaves and the rain this past weekend and doing yard work this past weekend, all kind of hitting at once. Um, but check out your Unit 1 exam grade, the updated grade if you haven't seen that yet. Uh, and the second note that I want to make is that this week we post midterm course grades. Um, so so just a really quick note on that. I could go into more detail, more depth on this, but kind of long story short, uh, how any individual instructor decides to give you a midterm course grade, it involves a lot of decision making on our part. So there's not like one tried and true method, right? Kind of what a midterm course grade is, it's supposed to be a statement about how you're currently doing in the course, but that's not very well defined. So you can think of it as something like if I had to guess what your final course grade would be, based on the information that I have now, if you were to continue working at the same, level of intensity throughout the course, what do I think it would be? Um, so that's maybe what it's trying to answer, but it's obviously, to answer that question requires making a lot of assumptions and so on, and kind of picking a model uh, for how we should answer that question. So what I'll do is basically just take a weighted average of your homework scores that were due to be completed on or before this past weekend and the Unit 1 exam grades. So I'll just weight together the Unit 1 exam grades with whatever weighting that is in the syllabus, along with your current estimate of your homework grades, your current average homework grade, along with whatever homework is weighted in the syllabus, and take the weighted average of those two. So that's how I come up with a midterm course grade. Um, what I would say definitely applies to this course, and I think probably applies to just about any course. Um, you know, if you think that you're doing B work and you see a midterm course grade of a C or you see a midterm course grade of an A, it's not meant to be that granular or that fine detailed. If you think you're doing B work and you see an F, there's probably a discrepancy somewhere, right? Either look and see if you missed some homeworks or something, or you missed the exam or whatever, and you didn't realize that, or reach out to me and see what the problem is, right? So something like an A or B, if that's your expectation, and you see a D or F on your midterm course grade, or vice versa, if you're thinking that you're doing terribly in the course and you see an A or B on the midterm course grade, that's meant to kind of give you a bit of a check in time that you can probably turn that around before the end of the course. But as far as like how granular plus or minus one letter grade, I wouldn't really be concerned about, but plus or minus a couple letter grades is probably something to be to either look into or to reach out to me or to do something about. So I met with our CCAC's lead guy for Proctor U. So Proctor U um, is the test proctoring system that CCAC is transitioning to. We're moving away from Examity, going to Proctor U. That implementation was to happen this semester. But when I talked with him last week, we kind of discovered that there are um, quite a few tech challenges with Proctor U. For some courses, it works great for the way that some courses are set up. The way that our course is set up with WebAssign, and Proctor U doesn't work so great with WebAssign. The way that our course is set up, it's implementing it is going to be quite challenging for a course like this one. So nicely enough, though, he said that they were able to keep Examity available to us through this semester. So we'll be using the tried and true Examity system. We'll be using just the automated system for the upcoming exams. So keep an eye out for I'm going to post an Examity practice exam and an announcement on Blackboard with some more detail about this. The Examity practice exam, the goal will be only for you to use this practice exam that doesn't count toward your final course grade or anything like that, to kind of get logged onto Examity, to get an account set up, to go through the process of making sure that all the tech works with, your webcam and all that kind of stuff. And to go into this, it's basically just a dummy exam with a few questions thrown in there. You go in there and fill in some answers or something, submit the Examity, or close out the Examity session. Just make sure everything works right. So I'll post that either this afternoon or tomorrow. So keep an eye out for the Examity practice exam and the announcement to go along with it. It's not an exam. It's not one of our unit exams for a course grade or anything like that. Just the practice getting onto Examity, onto the test proctoring system. And anywhere in the past that I've referenced ProctorU in the syllabus or anything like that, replace that with Examity. So Examity is going to be our proctoring system for this semester. I've used that for a few years now, and the automated system especially works great. Students very rarely have any problems with it. So I'm quite happy that we have Examity for one more semester, and we're delaying fully implementing ProctorU until at least next semester. Okay, and Examity will be used on all of the upcoming exams. So we didn't do proctoring for Unit 1 exam just because of the tech issues with ProctorU. And the quote of the day today, just really quickly, is by the Roman Emperor Marcus Aurelius, sometimes just quoted as B1, but really where that comes from is this longer quote, roughly translated as something like, stop arguing about what it means to be a good man or a good person, B1. So instead of, sitting around a table in your, comfy living room arguing about what it means to be a good person, or what it means to, to do this or that thing, or, instead of sitting around comfortably making a plan and never implementing it, get out there and implement it, take some steps forward. It's better if you take steps forward at 90% effectiveness or efficiency than if you take no steps forward and get to 99% efficiency. You would say, oh, well, if I had, started moving forward, I would have gotten further. But if you never move forward, you never get anywhere. Okay, so jumping into 5.3, multiplying polynomials. So the first thing we want to remember is our distributive property. So if I have something like, and again, we're kind of jumping right into this. This is review material, so I think this should all look familiar. But if I'm going too fast at any point, if you want me to, to slow down a little bit, definitely jump in and ask a question or ask me to go back over something. But the first thing we want to think about is our distributive property that says A times B plus C equals A times B plus A times C. When we have multiplication, multiplication distributes over addition. Also, we have a right distributive property. It works this way as well. So say 3 times the quantity x plus 1, I can distribute the 3 in and get 3x plus 3 times 1, or that's just 3. So I can multiply this out, 3x plus 3, and that's about as simple as it can get. Now, in the past, you've probably seen factoring. So we don't want to jump ahead, right? At this point, we're dealing with multiplying polynomials. So when we say simplify, we mean multiply it all out get a whole bunch of terms and then like combine like terms if we can. But we wouldn't want to say, oh, 3x plus 3, I can factor a 3 out and make it 3 times x plus 1. Well, that's just what we started with, right? So we don't want to go back and undo what we just did. So keep in mind the context of the section we're working in whenever whenever you're asked to do something like, for instance, simplify. Okay, if we have something like quantity x plus 1 times x, again, this x distributes to each of the two terms inside that binomial. We get x times x, or x squared, plus 1 times x is plus x. Now, something to be a little careful about, we tend to use the variable x quite a bit. And if we're not careful, sometimes an x can look like a times sign. In math, we tend to avoid after we get away from the very beginning levels of math, we tend to avoid using the explicit like time sign that looks like an X, except in very special circumstances. Like, for instance, scientific notation is a place that we really do use that. It's just part of that notation. Or another example is in calculus, there are some types of multiplication, some types of products that we use a multiplication that looks like an X. But we tend to avoid using times symbols that look like X's because they get, conflated. It's easy to confuse one for the other. So if you see something like this, almost certainly that's going to be 3x times x plus 1. In the context of algebra, we tend to use either just omitting the operation or maybe a dot to signify multiplication. So I want to take this monomial, 3x, this single term, the single factor that's multiplied here, and I want to distribute it through to the binomial to both terms. So I have 3x times x is 3x squared. And then plus 3x times 1 is plus 3x. My distributive property works more generally as well. I can distribute a monomial into a trinomial or into as many terms as I want. So for instance, 3x times x squared plus x plus 1. When I distribute, I just distribute my factor out in front to each of the terms, whether it's 2 terms or 3 terms or more. So 3x times x squared is 3x to the third power, plus 3x times x is 3x squared, and then plus 3x times 1 is plus 3x. Any questions so far? Now, an example like this, we have to be super careful. Here we have a z squared out in front, but it's a negative z squared. If I really wanted to be kind of pedantic, I could think of this as like a negative 1 times z squared, and I could distribute the z squared, and then later on distribute the negative 1. That's really, that's fairly inefficient to do. So I'm going to consider the negative z squared as just a single factor, just the opposite of z squared. And I'm going to distribute that to these 3 terms. So let me actually write out this distribution since this one's a little more complicated. So I have negative z squared times 3z squared, and then minus negative z squared times 2zy, and then plus negative z squared times 1. So we can always write out another step or two if that helps us keep things sorted out. In this first term, I see I have product of 2 factors. I have -1 times 3 gives me a -3, and then z squared times z squared gives me a z to the power 2 plus 2, or z to the fourth power. Over here I have, well, let's forget about the negatives for just a minute, but I have z squared times 2 times z times y. Well, that gives me a 2 z to the third power times y. Note that this is negative z squared, not negative z all squared. So this negative is not getting hit by that squared. This negative sticks around. And this negative is actually going to cancel out with that negative. So minus negative stuff is going to be plus 2z cubed y. And then, of course, over here I have minus z squared, or well, plus a negative z squared times 1, which makes a minus z squared times 1, or just a minus z squared. So multiplying polynomials, distributing is one of those things where I think the basic idea is pretty straightforward, but we just have to be super careful with all of the little details, right? Getting our exponents right, making sure that we use our exponent properties correctly, getting our signs right, all these little details as we're going through, we just have to take step by step and just be really careful to, to not be too flippant about things. I want to make sure that I have a property that we've discussed previously supporting every action that I make. So like I wanted to, multiply all of these together, and I know I have a commutative property of multiplication, so I can switch that z squared times 3 into 3 times z squared. Then I have z squared times z squared. I know I have an exponent property that says same base raised to powers multiplied together. I add the powers. So I get z to the power 2 plus 2 or 4, and so on, just going down the line. Okay, so what if I have something like this? If I have a binomial times a binomial, there's kind of two approaches here. The first is just to do what we kind of did before. We'll treat this binomial x plus 1 in front as basically one entity. It's just some parentheses, something, and we'll distribute it to the other parentheses. Well, what's that going to get me? That's going to get me that first thing multiplied by x plus that first thing multiplied by 2. And now I just have two copies of the same problem that we just did. Now this is right distributive, I suppose. I could rewrite it. I could switch the order of the multiplication around if I really wanted to. But here x distributes into x plus 1 as x times x, or x squared, plus 1 times x, or x. So this came from that first term. And then plus x times 2, or 2x, plus 1 times 2 is plus 2. These came from that second term up above. And now I want to simplify, and what I mean in this context is I want to combine like terms. There's no other x squareds, so it just stays by itself. I do have two terms that are x to the first power, or just x. Plus 1x plus 2x is plus 3x, and plus 2. Now, something that we might have noticed is that if we do this, we end up with four terms. This initial term here, x squared, I get by multiplying the first component of each binomial, the x times the other x. this plus x term I get by multiplying the inside terms, the 1 and the x, the ones that are on the inside are close together. The 2 times x I get by multiplying the outer terms or outside. And 1 times 2 or 2, I get those by multiplying the lasts. And my things are a little tiny bit out of order here, but this is called the FOIL method, first, outer, inner, last. So we get x squared plus 2x plus x plus 2 if we follow the FOIL strategy. Some people really don't like the FOIL method. The downside of the FOIL method is it doesn't generalize super nicely to harder problems or to bigger problems. But we deal with problems like this enough that I think it's a good trick to have in your back pocket. It's a little bit of a special case. It's a little bit less general than applying the distributive property, but it can save a decent bit of time if the problem you're working on falls into that category. This one does. It's a binomial times a binomial. It's a parentheses with 2 terms multiplied by another parentheses with 2 terms. So we can multiply our firsts, our outers, our inners, and our lasts. Well, that's x squared plus 2x plus x plus 2, or x squared plus 3x plus 2. So I don't really have an aversion to the FOIL method as long as we realize its limitations, as long as we realize that it really only handles special cases that look like this and not more general cases. We can make it handle more general cases. We might discuss that a little bit later here in a problem like this one. But when we try to force it to handle more general cases, it just ends up getting kind of messy. So I think that might be people's aversion to it, but I don't have a problem with it. So FOIL is best applied to the scenario where we have something like this, binomial times binomial. Okay, so if we look at an example like this one, y plus 2 times 3y minus 4, my firsts are y times 3y. My outers, I want to be careful of bringing that negative along for the ride. So my outers are minus y times 4. My inners, 2 times 3y. And my lasts, 2 times negative 4. I handled this minus sign in 2 different ways here just to show that you could handle it either way. You could do plus a negative or minus, right? I could either think of this 3y minus 4 as 3y minus 4, or I could think of it as 3y plus negative 4, whichever kind of makes the most sense to you. It doesn't much matter which way you do it, as long as you don't drop that negative. So I would say do it the way that you're less likely to make an error. And for my first, y times 3y is 3y squared. I have minus 4y plus 6y is a plus 2y, and then minus 8. Any questions so far? Oh, and I forgot to write my L for lasts. You could just as well have gone through and did the distributive property. You could have taken this first binomial and distributed it to the second, or vice versa. And then you'd have had to distribute twice more. You'd have gotten the same 4 terms, multiply things together, combine like terms. You'd have gotten the same answer if you did the distributive property 3 times, or if you did FOIL, this FOIL strategy. Okay, what about something like this? What if we have, these were nice, these were kind of linear binomials. We just had y to the first power terms and constant terms. What if I have a more complicated polynomial? How does that work? Well, the good news is it doesn't much matter what the degree of each polynomial is, as long as I have binomial times binomial, it's the same structure. It doesn't matter if this is 3x to the 10th plus, x squared times 2x to the 5th minus 3x to the 4th. The structure is the same. What really matters is that it's two terms multiplied by two terms. What's in those terms is of less importance. So because it's binomial times binomial, I can use the FOIL method, or I could distribute. I could go either direction. I use the FOIL method. My firsts are 3x cubed times 2x. My outers are 3x cubed times negative 3. I'm going to choose to think of this 2x minus 3 as 2x plus a negative 3. For me, I think that that's a little bit less error prone than the other way, although I think they're pretty close for most folks. My inners are x times 2x. And my lasts are x times negative 3. Right. This way, I don't have to deal with plus or minus signs while I'm trying to multiply the terms out. I just put all the negatives in the terms, and I'll deal with the plus and minus signs later on. So for my first, 3x cubed times 2x, 3 times 2 is 6. X cubed times x, well, that's x cubed times x to the first. That's just x to the fourth. For my outers, I have 3 times negative 3 is negative 9 or minus 9. Then I have a factor of x cubed, no other x's to combine with it. It just stays as an x cubed. That's a cubed. There we go. For my inners, I have x times 2x. Well, that's just 2 times x times x. I can use commutative property of multiplication, and that gives me 2x squared. And then for my lasts, negative 3 times x is just minus 3x. I have no like terms here, nothing to combine. So that's my answer. Any questions so far? Okay, let's look at this next example then. Again, here I have something that looks complicated. I have two variables, in this case, a and b. What effect does that have? Well, I still have just a binomial times a binomial. I have two terms multiplied by two terms. Same structure here. The details of, when I take each term and multiply things out and combine common factors and so on, they might look a little bit different, but the overall strategy looks the same. So I'll start with my firsts, 3ab times 2a. Then I'll move to my outers, 3ab times b. My inners, negative 2 times 2a. And my lasts, negative 2 times b. Okay, so I've got my FOIL done. I've got my individual terms all figured out here. I just need to simplify each term and then look to see if I can combine anything. 3ab times 2a, well, I can multiply the numbers together. 3 times 2 is 6. A times a is a squared times b. Right, this commutative property of multiplication, I can reorder multiplication. That's really coming in handy here. That's why I'm able to push that 2 out front move those a's together and so on. For my outer term, for the 3ab times b, well, that's just 3 times a times b squared. For the inner bit, negative 2 times 2a, I multiply the two numbers and I get minus 4a. And then my last, negative 2b, that's just what that is. Any questions so far? So hopefully this is looking a little familiar, ringing some bells, definitely up here, but maybe we're going a little bit deeper into it with some of these more complicated examples, maybe than you had seen before. So, the progression of 090 to 108 to 111 to 142 or pre-calculus, we cover a lot of the same material in each of those four courses, but it's a question of what's the depth of the material, how difficult are the problems that we're looking at, and so on. So we might cover multiplying polynomials or factoring, but from kind of several different points of view, several different levels of depth. Okay, now what about something like this? So could I apply FOIL here? I kind of could. Notice that I have a binomial with two terms multiplied by a trinomial with three terms. What I would have to do if I wanted to apply FOIL here, I would have to artificially group together some of these terms to make this feel like one term and a second term. So when I did first, I would have to do 1 times 3y squared plus y. And then I'd have to distribute. I mean, you don't have to distribute because it's a 1, but in the more general case, I would have to distribute this 1 again and so on. So I could use FOIL here, but it's really kind of a tortured use of the technique. So this is one of the reasons why some folks don't like FOIL. Some instructors don't like teaching the FOIL method because it doesn't generalize, at least not nicely, to problems like this. So instead of trying to force the issue and use FOIL where, it's not so helpful, or it might even be more of a hindrance than a help, I'm just going to use my distributive property. Typically what I'll do is I'll take the smaller polynomial, the one with the fewer terms, and distribute that into the bigger one. That's the way that I like to do it. I mean, it doesn't matter a whole lot which direction you do it, though. You could take this one and distribute it to each of these two terms over there. But I would rather go the other direction, just kind of my preference. So I would take 1 minus y times 3y squared plus 1 minus y times y plus 1 minus y times negative 4. If I can draw my y. There we go. Now what do I do in each of these three terms? I need to take a factor and distribute it. Right? There are lots of steps to do, but the strategy is similar. The strategy is really the same strategy fundamentally as a very simple problem like this one. Just distribute, multiply out, and simplify, combine like terms. We're doing the same strategy here. The overall, 30,000 foot view is exactly the same. And just the details are a little messier, a little more complicated. Okay, so coming through here, I have 1 times 3y squared is just 3y squared, minus y times 3y squared is 3y cubed. That takes care of this first bit here. Plus 1 times y is y. And then plus negative y times y is minus y squared. That takes care of the second bit here. And then my third bit, I have plus 1 times -4 or -4. And then plus a negative y times -4 is plus 4y. Okay, so I have a bunch of different, different powers on my variables here. I think I'll start by looking for the highest degree terms and work my way down. So I see I have a cubic, I have a y cubed. I don't see any higher power than 3. I don't see a fourth or a fifth power. I don't even see any other third powers. So this -3 y cubed will just kind of come down. I see I have some second powers. I have two terms that are second powers, one with a coefficient of 3, the other with a coefficient of -1. So 3y squareds minus 1y squared gives me 2y squareds left over, right? So plus 2y squared. If I have 3 of something and I lose one of that thing, I have 2 of them left over. That applies to apples or oranges. That also applies to y squareds. Oh, how did I do that? Trying to here. Oh, that's nice. Move left. All right, good. Okay. I also have y to the first powers, or just y's. I have 2 of those. I have plus 1 of them and plus 4 of them. So that's plus 5y. And then lastly, I have one constant term, no other constant terms for it to combine with, just the -4. Any questions, any thoughts on this one? Okay, so even a complicated problem like this one, there's just a lot going on. But again, the strategy is the same. The strategy for all of this multiplication um, is really the same. Just use the distributive property. And then just be really careful with, your signs, your exponents, with combining like terms carefully, all of that kind of stuff. Um, so there's a lot of moving parts. There's a lot of things you have to be careful with, but I don't think any groundbreaking new mathematical ideas. Okay, what about a product like this or like this one down here? These are what are sometimes called special products. These are products that work out quite nicely. If I FOIL this, I see for my first, I get 1 times 1 or 1. Let me actually write this out, 1 times 1. My outers give me plus 1 times y. My inners give me plus -y times 1. And my last give me plus -y times y. But this gives me 1 times 1 is 1. And then plus 1 times y minus -y, minus 1 times y. So plus y minus y, and then minus y squared. I actually noticed that my inner and outer terms, these what are called sometimes cross terms, perfectly cancel out. And I get 1 minus y squared. I get a much more simplified form. In fact, anytime I have a plus b times a minus b, my firsts are going to give me a squared. My outers are going to give me minus AB, and my inners are going to give me plus AB. They're going to cancel out. My lasts are going to give me B squared. So this general pattern pops up. I have the difference of squares product. A plus B times A minus B simplifies out to the difference of the squares, A squared minus B squared. And then I have products like this that are perfect squares. X plus 2 squared, be really careful. This is not x squared plus 4. We cannot distribute an exponent into a sum. Exponents and addition are 2 levels apart on the order of operations, and just the distributive properties only take us one level. So we don't want to be naive here and just try to distribute that squared into the two terms. We need to do x plus 2 times x plus 2. And we FOIL this out. We get x squared from the firsts, plus 2x from the outers, plus another 2x from the inners, and then plus 2 times 2 are 4. I see these combined together, and I get x squared plus 4x plus 4. It's a little less of a nice result than the previous one, but I might see that if I have a plus b all squared, that's a plus b times a plus b. My firsts give me a squared. My outers are plus ab, but my inners are exactly the same, plus ab. For these perfect square, these perfect square polynomials, the outer and inner terms always end up being exactly the same with the same sign, rather than where up here I had the outer and inner ended up being exactly the same, except with different signs. So I have a plus AB plus another AB, that's plus 2AB, and then plus B squared from the lasts. So that's another good pattern to recognize. Any questions so far? Okay, then moving on to dividing polynomials. So we have a couple of different strategies here. One of them is if we're dividing a polynomial by a monomial, by a polynomial with only one term. So something like 5 would be, well, that's just the number, but we can also think of it as a monomial. Or something like x or something like 5x, those would all be monomials. And it's really a very different process and feel. The deeper theory is the same no matter what, but the feel and the process of simplification is much different if we're dividing a polynomial by, say, a binomial, by something with more than one term. If I can select this here, this x minus 3 or this x plus 2, they almost feel like two completely separate problems. Of course, they're linked. Of course, they're doing fundamentally and theoretically very similar things, but the process of how to simplify is quite different between the two cases. So we'll look at monomials first. These are pretty straightforward to simplify. And then we'll look at dividing by binomials, and we'll look at polynomial long division and how that works. Okay, so dividing polynomials. So if we take, for instance, 15x squared plus 10x, all divided by 5, how can we simplify this out? I suppose there's two approaches we could take. One is we could use a fractions property that a plus b over c is a over c plus b over c. So I can break my fraction up this way. I can think of this as a numerator over a common denominator and break that apart into two fractions. And now I look in my first fraction, do I have a common factor in the numerator and denominator? I actually do. I have a factor of 5 in both. That just leaves me with 3x squared. And in my second fraction, I have a factor of 5 in that 10 times x. 10 is just 5 times 2. It's also possible, and this might be considered jumping ahead a little bit, or it might be considered something that you might have just kind of recognized as a pattern. So this is a perfectly acceptable way to go about this problem. Split it up into two fractions and simplify each of them. But you might have noticed that, well, 15x squared plus 10x, I could write that numerator as 5 times 3x squared plus 2x. And now I can use the common factors property of fractions that if I have, let me use different letters. If I have d times e over f times e, that's equal to d over f, right? I can divide out common factors. The same thing I did up here with the 15 over 5 or the 10 over 5. This would be like d, and then in the denominator I have 5 times 1. This would be like f, and my 5s can divide out, leaving me with just 3x squared plus 2x. So I kind of did these two steps all in one step down here. If you see that pattern, if you saw that pattern, feel free to use it. If you didn't see that pattern, and you say, wait, how did that 5 come out of there? Aren't we putting things in? Aren't we looking at, for instance, up here, using the distributive property? And the answer is yes, we kind of use the distributive property in reverse here. Again, if you see the pattern in a problem like this, or if you're good at factoring in general and you can just factor the numerator, you're, welcome to use that. But the more straightforward approach is to break this into individual fractions. And then within each fraction, everything is multiplied and divided. We're kind of staying on the same level of order of operations. Everything works a little bit more nicely. What I do not want to do, give myself a little more space here. What I do not want to do is start being too flippant with the operations I'm performing. I don't want to take 15x squared plus 10x over 5 and do something like this. Right? We see that does not get us the same answer. It does not get us the right answer. I don't have a property anywhere that says I'm allowed to do this. I have a property that says I'm allowed to do this, but importantly, there are timeses in both the numerator and denominator. My numerator in this property doesn't look like something times something plus something else times something else. That's not the form that this property has, right? I'm not using this property. I'm not using this property. I'm not using any valid property when I do something like this. I'm making up my own property, and it's inconsistent with the rest of the properties that we've developed. So we don't want to just be too flippant and start doing things like this. We need to keep in mind, what are these properties? If you're having trouble keeping these properties straight, there are a lot of them, things with exponents, things with fractions and all that. When you come up on a new property that you forgot about, maybe you forgot about this property, for instance, write it down on an index card, on a note card, and flip through your note cards once a day or something. If you have 5 of them or 8 of them or something, flip through them once a day, and just make sure that you're keeping them in front of your eyes every once in a while. If you have more of them, if you need a little more review, if you have 30 of them or so, maybe a couple times a day, flip through half of the deck or something like that. So what about something like this, 15x squared plus 10x over x? Instead of a denominator being just a number like 5, it's x, a variable, but again, very qualitatively similar. The number 5 is just kind of we can really think of it as a monomial, as a polynomial with one term. It's kind of just a number, but if we really wanted to, we could think of it as just a constant term monomial. Well, this is just a monomial that has the variable term. We can approach it the exact same way. We can apply this property of fractions. I can break my fractions apart. That's a property of fractions. It doesn't matter whether we're dealing with constants or variables or whatever. This works for all fractions. And then I notice that there is a factor of x in both the numerator and denominator that can divide out, leaving me with 15x. Right, 15x squared is 15x times x, and x on the denominator is 1 times x. These x's divide out, leave me with 15x divided by 1, or just 15x. And similarly, the 10x over x, the x divides out in the numerator and denominator, plus 10. What if I had an even more complicated monomial, 5 times x, that I want to divide this by? I do the same thing. Strategy is the same. The details might look a little different. There's quite a bit going on here. Let me take one more intermediate step. 15 I'll write as 3 times 5. And x squared I'll write as x times x. And 10 I'll write as 2 times 5. And now I see this 5 divides out with that 5. Again, that's just using our common factor property of fractions. This x divides out with, say, that x. This 5 divides out with that 5, and that x with that x. What am I left with? I'm left with 3 times x. Be a little bit careful. It's not like divided by 0. We always kind of implicitly have a times 1 on any series of factors. So it's 3x over 1 or just 3x, plus 2 over 1 or just plus 2. So even if I have a somewhat complicated monomial like this, or even if this was a 5x squared, I would take the same approach. I would split it into component fractions where each fraction is just a numerator that's one term. It's a bunch of stuff multiplied together, over a denominator that's one term, that's a bunch of stuff multiplied together. And now each fraction only has, like this one here, only has multiplications and divisions. This one only has multiplications and divisions. I can simplify each fraction individually. It's easy to do because everything is multiplied and divided, same level of order of operations. Easy to work with these kind of fractions. And then I can kind of glue everything back together at the end. And that's my answer. Sometimes I will be left over with a fraction at the end. Sometimes I end up getting rid of all the fractions. The denominators all kind of divide out like happened here. So when I'm dividing by a monomial, I have the ability to break up my fractions in such a way that each fraction that I'm left with only has multiplication and division. If I try to do that here, where my denominator is a binomial, I could get something like x squared over x plus 2 plus 8x over x plus 2 plus 12 over x plus 2. This would be allowed. This is a valid mathematical statement. This is an equivalent expression. But notice that each of my component fractions does not only have multiplication and division. We're really inherently stuck with an addition from that denominator. There's no way I can't do something like x squared over x plus x squared over 2 or something like that from this first fraction. There's no way for me to break this x squared over x plus 2 into two fractions where I only have multiplication and division going on. So the same strategy actually doesn't work here. Even the 30,000 foot view, it's, we do have to change something here. So even though this is a valid mathematical operation, I could do this if I wanted to, it just doesn't actually help me solve this problem. So not that it's incorrect. It is correct to say that no, this step is incorrect. This step is a fine mathematical step, but it just doesn't get us anywhere. So we don't want to take that approach. So what approach do we take? Well, the approach that we do take is polynomial long division. And so next time, we'll review regular long division just with numbers, remind ourselves how the process works, why it works the way that it works. and then we'll do polynomial long division. This is something that has a lot of steps. It might not be a bad idea for you to read through the material before next class meeting, maybe even watch a YouTube video or something on it. I might even, if I remember to, post a YouTube lecture or post a YouTube recording of one of my previous lectures from a different course. And yeah, so maybe prepare yourself a little bit ahead of time for this next time, because it's one of those things where there's just a lot of steps, and seeing it once or twice and kind of knowing where we're headed can make it a little more manageable. Okay, let me stop the recording.